So when we finish up here with compound inequalities on our second day, I really want our focus to be making sure that you understand special cases when it comes to compound inequalities. They can take a little bit of, additional thinking. So I want to make sure we see some examples and that we understand what those might look like. Okay, so specifically, we're still talking about compound inequalities, but we're going to focus on what happens if we have special cases. Now, just as a quick review, initially I mentioned that typically, most of the time, when you have an AND statement, those guys are going to shade toward each other, and so they'll have endpoints, and it'll just be kind of, the solution would just be the area or the space between them. And when we had OR statements, most of the time, those guys shaded away from each other. That's kind of your traditional, normal version of the and the OR statement. So today we're going to explore how we interpret our solutions if they happen to perhaps both shade in the same direction or contradict, the solutions maybe contradict the original statement. So that's what we're going to talk about here, okay? So when this happens, most of the time when we have a special case, it's that they both end up, the two inequalities end up pointing or having their arrow to the same direction. So I want to remind you that in an AND statement, right, we're only interested in the region where the solution is true for both. So in this little example up here, I'm not going to go through every detail. Let's say that we had this AND statement, and we simplify it and we solve it, and we realize that on one side of the AND statement, the solution is all the x's that are less than -1. And on the other one, the solution is all the x's that are less than or equal to 9. So individually, this is a solution to one part of it. This is a solution to the other part. But we are interested in an AND statement only in the overlap, right? Only where they overlap. So you have sort of three regions. You have everything over here above 9, which does not work in either one of these, right? Anything greater than 9 it fails both of these, right? Then you have this region right here in the middle that is true for this one, but not for the second one. It's true that, if I pick 4, for example, yes, that is less than or equal to 9, but it is not also less than -1. So we don't want that region either. We would really need just this region past this point right here, just like they marked, where they start to overlap. And so in an AND statement, sort of the shorter arrow, the inequality that kind of gives you the shorter arrow where they're both true, that really becomes the only answer to that compound inequality. Okay, and that's in an AND statement. If it were an OR statement, then our solution would have started over here, because as long as it's true for one or the other, then then we're all set. So above 9 doesn't work for either, but starting at 9, it's true for at least one, and so everything after 9 would have worked. So that's the big difference between how to interpret an AND or an OR statement. So let's take a look at that OR statement a little more carefully, right? We have this one already done for us for an AND. Let's take a look at number 11 and see what happens here. It's telling us to solve the compound inequality and graph it. Here is our OR statement, so kind of keep track of this. First of all, it's an OR statement, and this is also separating the two inequalities. So I'll go ahead and start working each one individually and find the two inequality boundaries here, okay? So on this one, I, of course, combine like terms first. So I've got a 9 and a -4. That's going to be a 5x with the -5 is greater than or equal to. And then this side is already simplified. Then I will gather my variables. So I'm going to, because I like to keep things positive, especially with inequalities, I'm going to eliminate the x term on the right. And that is going to leave me with 2 x's on the left, along with the -5, and that is greater than or equal to, and then 5 is all I have left on this side. And then we can actually start to solve for x. I start to now isolate this by doing the inverse of these operations. So I'll add 5 on both sides. That'll cancel the constant. And I'll finish this off, that's a 10, by dividing by the 2. And that effectively isolates our variable. Okay, So one of the inequalities in my OR statement is everything that is greater than or equal to 5. So I'm going to put a pin on that. I'll come back to that in just a moment. Okay, now let's go ahead and do the other side of this OR statement. Here I do have a grouping symbol, so I'll distribute. 2 times 3x is 6x. 2 times 1 is still 2. Is greater than or equal to 5x. Okay, if it helps, maybe make a little boundary here so things stay organized for you. All right, then next is gather our variables. So I could gather them to the left or to the right. I could move these guys to the right since sometimes we're a little nervous to not leave anything here, but that's going to make it negative. I really don't want to deal with that. I also like my variables on the left when possible. So I'm actually going to move this one. You might be being like, but there's nothing left. That's okay. We're just going to put a 0. That's what zeros are for. Okay, so I'm going to move this guy. Cancels it on the right side. 6x minus 5 leaves me with just an x. Is greater than or equal to, and since I have nothing here, the way that we say nothing in math is with a 0, and that is okay. This is still a totally perfectly valid inequality. And now we can go to step 3, which is isolate x. So we'll take away 2 on both sides, leaving the x alone. Turns out that x is greater than or equal to negative 2. Okay? All right, now let's go ahead and graph each one of these, at least for now, separately. Okay, because it's an OR statement, so anything that is true for one or for the other is going to be fair game here. So if I go ahead and say, okay, well, let's graph. Let's make our number line here. Maybe I'll start with a negative 3, negative 1. This is 0, 1, 3, 5. Okay, so let's take a look. If we graph everything that is greater than or equal to 5, that's going to be all the way over here. That would graph here with a solid circle, and we would say anything greater than or equal to 5 is a solution to this OR statement. But also anything that is greater than or equal to negative 2. So then I have to come over here to negative 2, also a closed circle. And that's also greater than. So I also make my arrow to the right again. So, but what is really the solution to the entire OR statement? Well, as long as it's true for one or the other, then it's fine. So pretty much everything over here fails both. But starting at negative 2, then we have numbers that are true in at least one of these. And for an OR statement, that's all you need is at least one. So starting right here, like if I picked 0 and I say, is 0 true for this one or this one? The answer would be yes. True is 0 works in here. 0 is greater than or equal to negative 2. So it works in at least one, and that is all that needs. That we need for an OR statement. So our final answer would be the longer arrow because it's an OR statement. So as long as we have points that are true on one of the inequalities, they are true for the OR statement, right? So that would be our final solution, would be this one that includes more numbers. That would be our solution. Versus over here in the AND statement, right? It was the more sort of exclusive or short one where it has to be true for both. So even this group right here wouldn't work on an AND statement, okay? Because it's not true for both. It's not true for this and that, right? But on this one, this is totally a fine section. The one that only has solutions for one is okay in an OR statement, okay? So hopefully that helps. Let's try another one. We're not going to do all of these. Let's flip it over and try number 13. This one I think is pretty interesting. So I'm going to give you a few examples here on just some that are kind of weird or fun to do. I think they're fun. All right, let's try number 13. So this is an AND statement. I always think it's really important to sort of acknowledge what kind of statement you're looking at, so that you interpret your answer correctly. So that's pretty important, okay? So it's an AND statement. Keep that in mind when we make decisions about our answer. But other than that, for now, I'm just gonna solve each one separately. So I'll start on this side. That long division is a grouping symbol, so I have to get rid of the denominator first. Opposite of dividing is to multiply both sides by 3, right? And on the left, multiplying by something that you already had been dividing cancels. We get 7x minus 5, and that's already looking better. Or equal to 3 times 3, which is 9. And I don't have to worry about flipping inequalities here because I have not multiplied by a negative, so all is good. And then I don't have variables on both sides. I don't have to worry about that, so I really can start isolating x. So I will start off by getting rid of our constant. There it is. So we get 7x is greater than or equal to the sum of 9 and 5, which happens to be 14. And then last but not least, we get rid of the 7 by dividing on both sides. So this part of this AND statement says that the solutions for this section of it are any x's that are greater than or equal to 14. Okay? And then we're just going to, like I said before, put a pin on that. And we'll go back to it in just a moment. Did I say 14? Wow, I can't believe 14 divided by 7 is 2. Did y'all know that? I knew that. Okay, so we're going to just put a pin on x is greater than or equal to 2. Thank you very much. And then we'll solve the other one, and then we'll interpret our answer. Okay, so this is one of the prerequisites or requirements to be a solution. All right, let's go to the next one. Nothing to simplify. I don't have grouping symbols. I don't have like terms, but I do have x's on both sides. So in step 2, we know we gather our variables. So again, to avoid negatives, I like to avoid negatives when possible. I'm a positive kind of person. I'm going to eliminate the x term on the left with a negative 3x. So that's going to eliminate it on the left. That's going to leave me with a 1 is greater than or equal to 4x minus 3x, which is just an x, and then minus 1. And then the next step, I will isolate x by getting rid of that constant with a positive 1. So 1 plus 1 is 2 is greater than or equal to x. I really do not like the way that looks, so I am going to go ahead and rotate that statement so that it is a lot easier to read. So our solutions are any number that is greater than or equal to 2, and also, like this answer here rotated, less than or equal to 2. So, let's look and see how this graphs, right? So I'm going to graph each one individually like we did a minute ago, and then I'm going to see where they overlap, because only where they overlap is allowed since this is an AND statement. So let's say that I decide to put the 2, right about there. And so the first one is anything greater than or equal to 2. So that means a closed circle and an arrow to the right. And also it needs to be less than or equal to 2. So that one would be a closed circle and an arrow to the left. But I only can use where there's overlap. And so this is a very interesting example here. Okay, if I think about, well, what numbers are greater than and or equal to 2 and also less than or equal to 2, the reality is there's only one number that makes this true. Again, the overlap. This has literally, it's a very rare inequality that truly has just one solution, x equals 2. So x equals 2 is the only value that can meet both of these criteria simultaneously. And that's the big game when it comes to special cases. All right, let's try one more. We'll try number 14 here. So number 14 is an AND statement. Keep that in mind. And we'll start solving each one separately. Starting on this one, I don't have grouping symbols or like terms that I need to combine on the left or the right, but I do have variables on both sides. So you probably are starting, hopefully, to get the idea here. But we have to take one of these x terms and eliminate it with the opposite sign. And again, I like to keep it positive if it is ever possible. So it's going to be this one, at least for me. That leaves me with just negative 18 on the left because the x's have been eliminated, is less than. And on the other side, 4x's minus 3x's is just 1x with the negative 23. And now I have only x's in one location. Now let's get that x by itself by adding 23 and eliminating that constant. Hooray for pencil. Like that. Boom. So when we simplify negative 18 and positive 23, my signs are different. So I'm finding the difference. That's going to be a 5. The symbol stays put, and I have an x. I do not like the x on this side, though. I think we've established that, so I'm going to rotate this statement and say it's really x's that are greater than 5. So that is one of the criteria for our AND statement, and let's find out what else we need for our AND statement. On the other side, check to make sure both sides are simplified. Check to see if you have variables on both sides. I don't have any of those situations, so I'm ready to solve for x. I will add 16 on both sides to eliminate my constant. I get x is less than, again, different signs, I find the difference. This is going to be a difference of 6, and it's going to be negative. Since I had more negatives, that the difference stays negative, okay? And so I'm looking for x values that are greater than 5 and also less than negative 6. So if I graph each one of those individually, one of the solutions in this AND statement is any x values that are greater than 5. So let me go ahead and graph this. I'm going to put the 5, 4, 3, 2, 1, 0. I don't know that I'm going to have enough space here. Maybe we'll count by. Let's try that again. All right, so maybe if I put a 0, 2, 4, 6, 8, and then negative 2, negative 4, negative 6, negative 8. That might be better. Okay, so one prerequisite is that the x's have to be greater than 5. So 5 is going to land right in between these. Greater than means open circle and a right arrow. The other prerequisite is that they also have to be less than negative 6. So that means open circle on negative 6 and a left arrow. And I'm only interested in solutions that make both of these true. In other words, where these guys overlap. Okay? Do they overlap at all? The answer is no, right? The answer is no. I don't have any numbers that can be at the same time greater than 5 and also be less than negative 6. So there's nothing that meets this criteria. There is no overlap in our graph. So this has no solutions. Okay, so that gave you a good hopefully a good taste of some of the and or statements. And then of course we'll talk about more of these in class if needed.